Okay, so this is called L'Hopital's rule. So it's set up as something that you're not able to find using direct substitution. So this is our goal, is to figure out what this value is right here. So I know this is a little flashback to our limits chapter, but it uses derivatives to actually make limits a whole lot easier. People always ask me why I didn't teach you this before, and it's because we didn't know derivatives before, so I was not able to teach you the shortcut while we were in the limits chapter. So this is the end goal, is to figure out what this is. So if you try to do substitution, if you plug a in, this is saying f and g are both 0. So if you sub a in, you would get 0 over 0. That's known as an indeterminate form. So when we were doing this with limits originally, I told you guys that that meant you had to do some sort of algebraic manipulation. And if you're able to, and if you want to, you definitely still can do this, but this method is super easy and super quick. So L'Hopital's rule says this: if you sub in the a and you sub in the g and you get 0, if f and g are differentiable on some interval containing a, so as long as it's differentiable at that point, and as long as the derivative is not always equal to 0, as long as a is not, or as long as x is not equal to a, so as long as it's not 0 anywhere else, then here's what our L'Hopital's rule says: the limit as x approaches a of f over g is equal to the limit as x approaches a, and then what we do is a super quick trick. We take the derivative of f, we take the derivative of g. The reason that I like to separate this away from the product and quotient rule a little bit is because I keep trying to tell you guys that the quotient rule is not just the derivative over the derivative, and that's exactly what this is. So make sure that you are not confusing this with the quotient rule. This is not the derivative of this quotient. It's replacing the numerator with its derivative, replacing the denominator with its derivative, and it makes this nice little trick. So if we were to look at this example right here, first of all, you always need to confirm that this is true. So you need to, sorry, it was off the screen. You need to confirm that this is true, that you're actually able to use L'Hopital's rule before you go through and use it. So this one right here, if I try to sub in 0, so we're gonna go for the direct substitution. I have the square root of 1 plus 0, and then minus 1 over x, which is 0. So of course the square root of 1 is 1, 1 minus 1 is 0. So you do this quick little confirmation to show like, yep, L'Hopital's rule applies because I plugged it in and I got 0 over 0. You could also do limits at infinity with this, and if you get like infinity over infinity, you could use L'Hopital's rule as well. So that'll pop up in some of the problems you guys are gonna do. So we confirm that we can use L'Hopital's rule, and then we go through and actually do it. So you replace the numerator with its derivative, you replace the denominator with its derivative. So first of all, before I take these derivatives, I'm just gonna rewrite this numerator as 1 plus x raised to the 1/2 power, and then minus 1, because that'll make it easier to take our derivatives. So L'Hopital's rule, this limit expression stays the exact same, and then I replace this with its derivative, replace this with its derivative. So this first part requires us to do a chain rule. We have a 1 plus x that's subbed into a 1/2 power function. So we do the derivative part, which means the 1/2 comes out front, power drops down to a negative 1/2, and then this is the 1, sorry. Because that is a nested function, you have to multiply by the derivative of the inside, and the derivative of 1 plus x is actually just a 1. And then minus the derivative of 1, which would be 0, over, and then you replace the denominator with its derivatives. The derivative of x would be 1. So you replace the numerator and denominator with their derivatives. You are not taking the derivative of this entire thing as a quotient. That would require the quotient rule. What we are doing is just replacing the numerator and the denominator separately with their own derivatives. Then once you do that, you can sub the 0 right in. So we have 1/2, and then if we sub the 0 in here, this becomes 1 plus 0, which is just 1. Raised to the negative 1/2 power. I'm not going to write that we're multiplying by 1. I'm not going to write that we're subtracting 0. And then this is all over 1, so I'm not going to write that either. So this ends up being 1/2, and then 1 raised to any power is just 1. So our answer is 1/2. So the limit as x approaches 0 of this expression up here is 1/2. Because of the square root, we would have had to do a conjugate. We would have had to multiply top and bottom by root 1 plus x plus 1, multiply top and bottom, distribute, simplify this whole thing up. There would have been a lot of manipulation, and this is a fairly quick trick if you know your derivatives well. So let's look at the next one. Example 2. So when I go to plug this 0 in here, I have the sine of 0, which if you know your unit circle well, hopefully we know that is 0, and then over 0 squared. So sine of 0 is 0, 0 squared of course is 0. So we confirm that we're able to use this trick, because this trick does not work if it's not 0 over 0. Okay, I promise you it will not work. You'll get the wrong answer. So now we go through and we take the derivative. So the limit as x approaches 0. So we replace the numerator with its derivative. Derivative of sine is cosine. Replace the denominator with its derivative, and the derivative of x squared is 2x. And then we do direct substitution again. So we are going to plug in the 0. So cosine of 0 is 1. And then over 2 times 0, which gives us 0. So we end up with 1 over 0. So we're not able to do that either. So what we're going to do is, this is not something that's actually defined, but we can't do Hopital's rule again because we got 1 over 0. So anytime that you get a number over 0, remember you do the tinies. We do the tinies and we separate out the left limit from the right limit. So we're going to do the left limit of this expression, and we are also going to do the right limit. Okay, so left limit. If we plug in 0 or something really close to 0, the numerator is going to be something that's really close to 1. All right, and then the denominator, if I plug in something that's really close to 0, it is going to be close to 0, but the important part is that I'm plugging in a negative tiny number. So if my denominator is a negative tiny number, when I multiply it by 2, it's still a negative tiny number. So remember, a positive whole number over a negative tiny number, that is headed towards negative infinity. So that's the first half, that's the left half. The right half, when I plug in 0, my numerator is still awfully close to 1. And then if I plug 0 into the denominator, 2 times a positive tiny number ends up being a positive tiny number. So that is headed towards positive infinity. So what that means is that this would be a vertical asymptote. The limit does not exist because the left limit and the right limit are approaching something different. So our final answer, we would say that the limit does not exist. All right, and our final example here, example 3. This requires some more unit circle knowledge. So this one is at pi over 2. So for the direct substitution, I'm going to sub that in. So I have the secant of pi over 2 divided by 1 plus the tangent of pi over 2. So I'm going to evaluate those. So secant of pi over 2, remember that is the reciprocal of cosine. So think through cosine. Cosine of pi over 2, that's like, pi over 2 is right up here, right? So the cosine of pi over 2 is 0. So the secant of pi over 2 is actually undefined. We're going to write that as 1 over 0. And I promise this will start to make sense in a little bit. Over, and then 1 plus, so now the tangent of pi over 2, that's at this spot right here. Tangent is sine over cosine, and at that point, sine over cosine is 1 over 0 as well. So this is 1 over 0. So now, fun fact, if we have 1 over 0, we typically consider that to be infinity. All right, or we could do like a little bit of rearranging here, flip top and bottom, but what ends up happening is we consider 1 over 0 to be like infinity, technically. And then this, if we have infinity plus 1, we still consider that to be infinity. So I mentioned this up here. Rather than 0 over 0, you could also get infinity over infinity, and we consider that to be an indeterminate form as well. Basically, all of this craziness is definitely an indeterminate form. So 0 over 0 or infinity over infinity, we can use this Hopital's rule. So Hopital's rule tells us that we keep the same limit expression as we started with, and then we replace numerator and denominator with their derivatives. So the derivative of secant is secant tangent over, and then the denominator, we have 1 plus, so the derivative of 1 is just 0, and then the derivative of tangent is secant squared. So before I try to plug anything in, I'm going to simplify that down first because I have a common copy of secant that I can cancel out. So if I cancel out this common copy of secant, I will have just a tangent in the numerator over just the one copy of secant in the denominator. And then I can try to plug it in again, but what's gonna happen is I know I'm gonna get 1 over 0 in the numerator and I'm gonna get 1 over 0 in the denominator. So let's keep manipulating this trig stuff. So limit as x approaches pi over 2. So tangent, remember, is sine over cosine. And then divided by secant, which is 1 over cosine. So if I'm dividing by 1 over cosine, remember it's really the same as multiplying by cosine. So if I take this and multiply it by cosine, what ends up happening is these cosines will cancel. So, fun fact, tangent divided by secant is actually just equal to sine. And if you think about it this way, since secant and cosine are reciprocals, if you're dividing by secant, it's the same as multiplying by cosine, which is its reciprocal. Just like dividing by 1/2 is the same as multiplying by 2. So since I divided this by secant, it's the same as multiplying by cosine, which would make the cosines cancel. So one last time, keep this limit expression here, and now it's just equal to sine, and I can do direct substitution, the sine of pi over 2, which hopefully we know our unit circle, sine of pi over 2 is 1. All right, so that is L'Hopital's rule. We're gonna have lots more practice with that, but the basics are, if you know your derivatives, you can make this rule work.